So we're going to bring on our next speaker, Alexander Conklin, head of hardware engineering at Rain AI. Alexander leads hardware efforts at Rain AI, a company focused on low-power AI accelerators, As one of Rain's early employees, Alexander built the architecture and assembled the design teams for the company. He's very, very passionate about cost-effective computing. And Alexander holds engineering and applied physics degrees from Johns Hopkins and Stanford University, respectively. Please welcome Alexander.
So I'll start out by saying thank you for having me, and thank you to Andes. It's great to be here. The focus of this talk will be to showcase what we call a RISC-V-centric approach to AI accelerator development. And we'll talk about some of the challenges in building custom AI accelerators, and especially with regards to the ISA and software. And we'll do this by walking through an example of how we might elect some operators that we want to accelerate and how we integrate them into our architecture and the RISC-V extensions that we'll use to program them, and the benefits of preserving some of the RISC-V vector semantics. One of the key insights I'll try to harp on and share is that using this approach along with the right simulators gives us a really nice medium for hardware-software co-design. We can have software engineers and hardware engineers explore different usage models of an instruction and get good data on utilization to improve the instruction. And I think some of these learnings have come from our experience over the past 18 months developing our processor. I'll start by giving a brief introduction of the company. We're Rain AI. Our goal is to reduce the energy of AI, and we build AI accelerators with record cost energy efficiency. We're 35, almost 40 employees based in our up the road in San Francisco. And we're a Series A company, 40 million to date. Notably, Sam Altman led our seed round, and we've been blessed to work with some really talented advisors. I'll start by motivating Rain's approach and what we're optimizing for. And I think that one way you can broadly define or an axis that kind of looks at the accelerator, the ML accelerator spectrum, is as follows. On the left-hand side, what you see is our general purpose, our more standard CPU and GPU hardware. We have well-established programming models, a mature software and compiler ecosystem, and it's general purpose hardware. So we can get pretty good performance across diverse workloads. At the other end of the spectrum, we have our fully custom AI accelerators, and often an ISA built from scratch. Often we start with a lack of an established programming model, and there's significant effort required to build out the software and compiler stack. But there are benefits. It's optimized for specific use cases. When those software tools do reach maturity, you are able to see these step functions, 10x improvements in performance or latency. Rain's approach lies somewhere in the middle, and we want to leverage the best of both worlds. It is one of our core competencies is in custom silicon design and building really performant accelerator blocks, but we want to leverage some of the software and programmability models that are available. So we build off an established RISC-V programming model. We create an AI ISA that kind of emerges naturally by extending the RISC-V ISA. We're able to leverage the things that RISC-V does well. It's open source. A lot of people care about software. There's LLVM. You can buy a RISC-V processor off the shelf today, and you can compile an AI model to its VPU. And that's a really good starting point. However, we also want to optimize for specific use cases without sacrificing some generality in the hardware. That is, if a new operator emerges or we see kind of an evolvement of a key AI workload, we don't want to be left in the dust. And with all of this, I think it goes without saying that it's in our interest to reduce our time to market. And that means leveraging tools that already exist. For those that might not be as familiar with AI, I think a good place to start is to ask ourselves, what are the features of workloads we're interested in? What are the applications? Like, what do AI workloads look like? And what I show here is a small snippet of a graph from a larger image segmentation or recognition model, YOLO V8, the you only look once models. If we stare at this long enough, we could start to glean a few insights. First, this convolution is really nothing more than a set of vector matrix multiplies. And we actually have 1,600 of them. And we use the same set of weights. So here we have an opportunity for some weight reuse. And we know that it's probably a good place to start by accelerating that block. We see a nonlinearity in the sigmoid function. And we see that this kernel in particular, and yellow's really, you could think of maybe 20, 30, 40 of these blocks pieced together. They have different shapes and sizes, but it's very representative. And we have these two smaller kernels, and our kernels can be pipelined. We don't need to fully complete that first convolution operator before we start the next stage of processing. There's also some data movement patterns that we can recognize and we may want to exploit and take advantage of. And as a point of reference, we can run this on a GPU, on a Jetson Nano. And we can start to kind of, this is a visual representation of where we might want to start hacking away at the problem. The largest part of the pie chart, and our biggest pain point might be these convolutions. We just have an immense amount of matrix multiply to do. So that's a good place to start. And we also have these element-wise operations, such as your add and mul, and your nonlinearity and sigmoid. A lot of these features, as you move to larger models, such as LLMs, are the same. Of course, you have this memory wall, and you can be memory bound. But when you're not memory bound, you have the same primitives. You have gems. In this case, in the case of LLMs, you have quite a wide range of arithmetic intensity that you need to support, whether it could be thousands in the prefill phase and then go down to single digit as you're generating your tokens. And you make more pervasive use of nonlinear operators, such as softmax. So it's a good starting point. To establish a baseline of performance and for maybe contextualizing, I think it's worth looking at how these might run on like an out-of-the-box RISC-V VPU with a VLAN of, let's say, 512. And while operators like ReLU might run well, as we move down to operators like the nonlinearities, depending on how you approximate them, these can be bottlenecks in your network. So some takeaways is that maybe exclusive use of the VPU may be insufficient for demanding AI operators. The VPU doesn't fully leverage good memory reuse for VMMs and gems, and nonlinear function approximations can be challenging and require many instruction calls. So what's the solution? This is where we leverage our strengths to tailor silicon to the operators. And for addressing VMM and gem operations, we leverage a digital and memory compute solution. And for things such as nonlinearities, we can use fixed function accelerators. Here, I think it's appropriate to kind of to step aside and talk about one of our strengths and something we're really excited to introduce, which is our custom in-memory compute macro. We have a custom silicon team, meaning we've designed the bit cell ourselves. We do layout ourselves. And what this does is it's an in-memory compute block. So you can think of having an SRAM-like array. You load your parameters into that array or the matrix values, and then we append logic directly to the bit cells, so you're able to do useful math. The key features of this that may distinguish it from other approaches is that we're able to tailor this for the arithmetic and the math that matters. It's tailored for these microscale formats, which you may have seen, these MX or int8. The key idea is you start with like a BF16 or a higher floating point precision vector, and you decompose it into a single scale factor and a vector of integer values. And it allows you to push the mapmul operation into the integer domain. And that's what our macro accelerates. And then you can drag that scale back later when you have the result and reconstruct your BF16 vector. It's bit accurate. There's no noise. This allows direct, with our choice of quantization, this allows for direct cast of AI models. And it's flexible for a wide range of requirements. If you have weight reuse, that's great. But you can also rewrite the array quickly in the case that you have lower arithmetic intensity. And there's power savings for sparse operations. On the right, you see kind of a complex of these macros that are in our Puget Sound accelerator, which is taping out in 2 weeks, and a summary of the technology. So it's TSMC 6 nanometers. It can store a matrix of 16 kilobytes, and there's 4 operational modes. The area comes in at just under 0.1 millimeters squared, and it's very performant. So if you have sequential int8, dense int8 operands you can achieve 46 TOPS per watt and go higher as you move to int4 operands and sparse operands. We also can build custom blocks for accelerating our sigmoid and our CLU functions. And if we revisit the table I showed you previously a few slides back, we use this for the sake of comparison, where we're able to get much more throughput with these kind of these targeted blocks, and it comes at a fraction of the power. And I think the key question now is we have the theoretical performance we need, and that's a requisite, but it's not sufficient. So how are we going to integrate these RISC-V or these blocks with the RISC-V core? And I think we can recall the slide I showed earlier, and some of the criteria, or our approach might be motivated by some of our challenges. We'd like to leverage a RISC-V programming model. We don't want to start from scratch. It'd be nice if there's already some established way of introducing, how we control these blocks into a compiler, and we want to reduce development time. So these kind of have big implications on, where do our units sit? Are they going to sit on like an AXI bus outside the core? Are we going to pull and integrate them into the core more closely? And what are the implications for the programming model and the instructions we use? Like, what does an instruction look like to control these blocks? And to be concrete, we make the decision to pull in, integrate our accelerator blocks into the core and tie it closely to the vector unit. We use custom RVV extensions to, particularly with ACE, to develop rich instructions to control these blocks. And these instructions look really nice. There's something familiar with them. They inherit the stylistic and semantic properties of your RISC-V vector extension. And this keeps the architecture pretty clean. And we can maybe avoid some of the challenges of you can imagine linking these blocks on an AXI bus and using more of a DMA programming scheme. Or at the very least, we could start here and prove ourselves that we may need something else. I think it's important to caveat this is a kind of an abstracted representation of a portion of our architecture. We're not going to review every custom instruction, but we'll focus on maybe two for educational purposes. So our in-memory compute is integrated using Andes streaming port. So we introduce a second vector load store unit. We have a lot of bandwidth. We provide direct access to the VRF, and we can leverage some custom addressing control to control a plurality of these, of what are effectively matrix units, very easily. For nonlinear operators, we use ACE RVV, and we create a register to a register instruction. It's tied closely into the vector pipeline, has direct access to VRF, and we have these support for these nice features like ELML, these pipelined multi-cycle instructions. And as a case study, I'd want to walk through how we create an instruction. And I put this together as an example. It's not something we have implemented, but this is also to illustrate what I think is a particularly serious and well thought out and thoughtful tool in Andes Copilot and how it can be leveraged. So let's say we want to introduce a nonlinearity like sigmoid. We start with two things. One is the ACE file, and this is how we're going to write our instruction. So there's a bunch of fields. I pick a few of them here. Like we start with our operands, which vector register is going to be input, output. A vector unit, are we operating dlen-wise or elen-wise? And then, you might have some secret sauce about how you approximate this function, and you write a kind of a C semantic description of this. And then further on, you then have to correlate this ACE file with your actual implementation of this hardware. So if you know if it's a pipelined implementation, you know your latency. You can specify your latency, and then we can specify an attribute for cycles per result that tells us when we group our registers, we have ELML of 4 or 5 that after that first latency, every cycle thereafter, I'm going to start seeing results. And we run these two files through Copilot, and we get a few really nice things. One, our updated core RTL with the new vector unit. So all this RTL surgery is done for us. Second, we get collateral for simulation. And we can build an Andes System C simulator for the instruction. We get, well, the instruction is generated along with these C wrappers, these intrinsics. And that's what I have in the image to the right. So you can see the actual instruction and then these wrappers, which are really, and we'll talk about this in a moment, which are really useful for writing and kind of playing with this instruction. And then we get compiler collateral. If we eventually when we like this instruction and we want to integrate it into LLVM, we have a way to do that. So I want to use this slide to highlight the simplicity of the instructions. And what I show is two instructions. One is on controlling our matrix units, our in-memory compute. And from a software perspective, these look like vector load store instructions. And this makes it really easy to play along, to program a plurality of these. And we have, because we've added that second load store unit, we have a lot of bandwidth. And our ACE RVV instructions is that ACE sigmoid, again, looks like a vector instruction. It looks like a register vector instruction. Both instructions abide by the RISC-V semantics of eleml, your element width, and you can even go beyond this and inherit support for masking and other features. And this is really nice. And this is where I think we can get into really what I think is the crux of the talk and the heart of the message, which is what can we do with this collateral that we've generated, and why is it beneficial to integrate our blocks in this more RISC-V centric fashion, and that comes to hardware-software co-design, and I think this kind of reflects some of our learnings. But we now have a way where we can quickly handwrite kernels of different AI operators. So we can explore the uses of this instruction, maybe to YOLO model, and then maybe in ResNet, and then eventually in an LLM, or a portion of an LLM. And because of this simplicity, we can take an atomic approach. And what I mean by atomic is that we can start with some code that just runs on a VPU right out of the box. And we can start pulling pieces of that code out and replacing it with our instruction. And we can walk back when we need to. And this provides, I think, and that's what I show on the figure on the left, is maybe you start off with this approximation that you run in the VPU. Okay, well, am I going to save cycles? Let me throw in my new sigmoid function, and I add it, and then I can compile it and run it. I can use my system C model. I can run it in RTL, which is nice for verification purposes, and I can get feedback on the performance and utilization and cycle count. And this provides really the true medium to do hardware-software co-design, because you put the ability and you lower the barrier to work with these instructions. They're expressive. They feel familiar, and you can cover more ground in exploring how the instruction is used. This is just, I think, what maybe the tip of the iceberg. What I showed was a very simple instruction, but if you have, if you want to improve performance and utilization, there's also other tool sets available to you. So you can introduce custom registers, custom memories, and you have the data to make informed decisions about how you might want to change an instruction or how you interface with a custom block. So in conclusion, we showcased how we can leverage the strengths of RISC-V and accelerator design. We can create these compute-rich instructions that feel very, very, very familiar to us. And ACE provides a nice tool set for doing so. The process of RTL surgery is handled for us, and we have this useful collateral. And if we use this collateral correctly, we create a nice playground in which we can do hardware-software co-design. And we can get kind of quick feedback and tangible feedback. Hey, it might make sense to fuse another operation in this instruction, or it would be really nice if we could have masking support here. And I want to end by saying thank you. It's been great working with Andes and getting to know some of the engineers. And thank you.
Any questions for Alexander? You have a question? Please raise your hand. Great. I'm going to get to this gentleman first.
I want some of these other instructions that you're talking about that people get to toy around with. Do you see any patterns to them? What do these higher level instructions look like?
What do you mean by higher level? Like how?
You got sigmoid, you've got stuff that you showed in convolutional neural networks. But are there LLM instructions in particular to LLMs, for example? Put a lot of C embedded technology stuff. Other application specific instructions that we might find interesting in the audience.
Yeah, absolutely. Normalization softmax are, I think, two pretty concrete examples that are pervasive in LLMs.
Hey, Alex, great stuff. Were you able to get a compiler to emit any of the new instructions, or were all the intrinsics instantiated manually?
Sorry, can you repeat the question?
Were you able to get a compiler to emit any of the new instructions?
So I think maybe I'll hand this over to our head of software, Rebecca, who can speak on this.
Directly from the compiler, but we also have an automatic compilation platform that maps operators, from the ML workload directly to those lower level instructions to get the most efficiency out of the box.
One more question. Do you find scalable vectors for putting out, or are you using fixed vectors?
We are using scalable vectors, and I think there's a little bit of exploration of whether, whether there's advantages to having fixed vectors, but at the moment, I think we're taking good advantage of scalable vectors. Yeah.
You mentioned that you're using a TSMC 6 nanometer process. I've only heard about a 7 nanometer. Where do you get a 6 nanometer from them?
It's a half node, so I think it's just an optical optimization.
Thank you.
It's very much available.
Back here.
Hi. You mentioned you're talking about in-memory compute. Can you say a few words of how you do the in-memory compute? Most of the time people talk about that in conjunction for analog computing.
Yeah, absolutely. I can contrast it with analog computing. That might be helpful. In analog approaches, the most common approach is that you store your array on some sort of like a resistive memory or PCM. And you store it in like a crossbar structure, and then you apply voltages and read currents, and you leverage quite literally Kirchhoff's laws to do multiply and accumulate. There are benefits to this approach, but a challenge. Oh, so our approach, I think to juxtapose that approach, we use a digital approach. So we have a custom bit cell that we've designed, and we maybe to stay high level for obvious reasons, we append logic to that bit cell. So we have an SRAM-like array with logic appended. So you can store all your weights in that array, and then you can drive bit serially your activations and accumulate.
Good enough. Thank you so much. Alexander Conklin, right here.